5.4 Types of reactions. Chemical reactions can be classified as combination reactions, decomposition reactions, single replacement reactions, double replacement reactions, and combustion reactions. And in this little section, we're going to hopefully help you be able to look at different reactions and predict them. That's the objective of this particular section. So, as we look at a combination reaction, the word kind of makes sense, combine. So that's when two or more elements combine together to form one product. So you will notice the generalization is, so here's our reactants on the left side of our arrow. Notice we have 2 and yields 1 total product. So that's the term combination reaction. So here's some different examples. We have magnesium plus oxygen gives us magnesium oxide. We have sodium and chlorine to give us sodium chloride. We're having sulfur trioxide plus water to give us sulfuric acid. So here's different examples of combination reactions. And here's a pictorial vision. Maybe it will help. So here we have our magnesium ribbon. It's magnesium metal. And when you burn it with some air, i.e. what's in air, oxygen, then the oxygen from the air is going to combine with the magnesium metal to yield a new compound, which is this white dusty-like stuff. And the new compound is represented in this pictorial image here. Now, just the opposite, if you have one item that splits into 2 or more products, that's a decomposition reaction. So it's just the opposite. It's decomposing. Rather than combining, it's decomposing. So we have a couple of examples. Notice we have one item and the 2 products. We have the 2 products here. We have another one example. We're going to have 2 products. You could have 3 products, but the key on decomposition is you're starting with one item and it splits apart. So again, a pictorial representation. We have one item with heat. It breaks it into the elements. Now on single replacement reactions, one element takes the place of a different element in another reacting compound. So here we have one element and it reacts with this compound, and this element goes in, and you will notice how it kicks out the representation of a B here, okay, of B, and it kicks that out, and out pops B, the other element, and A combines with the original anion part, in this case, and makes a new compound. So we are going to have our zinc plus HCl. You will notice that the zinc goes in and kicks out the first element of this compound, which is the hydrogen, and zinc hooks up with our chlorine and our chloride ion, and so you will note, and out pops hydrogen. So you'll notice, first of all, that the numbers are different here. Well, that's because when it does rearrange to form a compound, it does have to form a compound in the correct manner, just like we predicted how zinc would need 2 chloride ions back when we were naming compounds. Why? Because zinc is a +2 charge, chlorine's a -1, so we're going to need 2 of these to balance this out. And then, of course, that's why we need a balanced equation. But right now, we're beyond that. We're not now just trying to identify what type of reaction this is. So now, here's another example. We're going to have iron is going to go in and kick out the first element of this particular compound. Now you may say, oh, does it always go in and kick out the first one? Well, it depends. It only goes in and kicks out the first one on a single replacement reaction if it will form a positive ion. So because our zinc and our iron are both metals, they will form positive ions, i.e. cations. So that's why we know whenever we combine to make, for example, an ionic compound, then we're going to always put the positive one first. So that's why the iron goes in and kicks out the copper to hook up with the sulfate is because it becomes a positive iron, in this case positive 2, so iron 2 sulfate, and sulfate is a negative 2, so that's why this particular compound is written this way. Out pops copper. And here was an example of what we just mentioned. Here's our zinc, our zinc bar. You stick it in some dilute hydrochloric acid, and you'll notice in a little bit of time bubbles start appearing. And you leave it in long enough and it'll appear that the zinc is dissolving. Well, whatever you want to call that term, it is reacting and it is forming hydrogen gas. That's what these bubbles are, and the zinc metal is going into solution, and so it is rearranging. It's going in, kicking out the hydrogen of the HCl, and it connects. Then it's going to combine to make our zinc chloride and hydrogen gas. So again, the point here is that you can look at this and go, oh, that's a single reaction because one item went in and kicked out another item. As opposed to a double replacement reaction, that's when we have two partners that are going to be switching places. So notice here, our A comes in here, kicks out our C to hook up with D, and our C then switches places with the A to hook up with the B. And you may go, well, why over here is the alphabet A, D, and C, and B? Why isn't it, A, B, C, D? Well, first of all, this represents the positive side, this represents the negative side, positive side, negative side. So you know that when they go over here to combine, the two positives can't hook up together. So the only possible combination is that A is going to then, when it switches partners, is going to hook up with D. And C can only hook up with B. And then you go, well, why don't you write B before C because it comes first in the alphabet? No, these are just representations, and the fact that because B represents the anion, the negative part, and C represents a cation, a positive part, when they combine, the positive one is always written at the beginning of the compound, and the negative one is written at the end of it. That is why you have this representation of the C before the B. And so as we look at this, that may be hard to visualize as these just A, B, C, and D. But let's look at actually real compounds going under reaction. So we have our silver nitrate and our sodium chloride. You will notice the silver goes in and it exchanges, replaces the sodium. So the silver hooks up with the chloride ion, and then out pops sodium, and then we have the sodium nitrate ions there. So our zinc sulfide with hydrochloric acid. So our zinc will go in and kick out the H, just like just kick out the H. Now then, H doesn't just come out as H2 gas like in our last reaction, the single replacement. Why? Because with a double replacement, there is someplace else for it to hook up with. So it can then hook up with the sulfide ion. And so we have our zinc going to combine, replace the H. So we have our zinc chloride, and the H hooks up with the sulfur gas for our hydrogen sulfide. And so we have another example of this in a pictorial view to show when you're going to switch our partners, our replacement partners. Our sodium is going to go over here to our chlorine, and our barium hooks up with the sulfate. Now notice that you need to realize is that the numbers like the 2 here doesn't necessarily stay with it. Why? Because when it forms a new compound, it's going to arrange and have the right amount of charges to balance out. So that's why we have to then balance in front as coefficients. But the big part here is for you to be able to identify that this is a double replacement reaction. Now on a combustion reaction, that's just another name that we're going to use, essentially fire. Okay, so a carbon-containing compound burns an oxygen gas, and what's really might be interesting is that it does form carbon dioxide and water, which might be kind of weird to think that a fire produces water, but that is one of the byproducts. Now notice we're going to need oxygen as one of our reactants. So yes, we know that when you're going to burn something, we are also going to get energy. So you can include energy, but energy itself is not a compound. So if we're just writing the compounds, you don't have to write energy. So here we have our carbon base. This is our methane. So if you have a natural gas stove and you are turning it on to cook breakfast, then it reacts with the oxygen in the air, and the two compounds that it's produced besides energy is our carbon dioxide and water. That's how you can identify a combustion reaction, is you have oxygen with the carbon compound, and your two products are going to be shown as carbon dioxide and water. So here's propane, C3H8. So propane, when you're burning propane, you'll notice you need oxygen from the air, and so our two products are going to be CO2 and water. So let's see, press pause and see if you can classify these as to combination, decomposition, single replacement, double replacement, or combustion. All right, so you're back. Let's look at this. This is a single replacement because we have one element that's going to go in and kick out the hydrogen. So the one element hooks up with the sulfate. Here is going to be double replacement. Why? Because we have an element of this reactant and an element of this reactant that switch partners. So our sodium goes in and kicks out the silver, hooks up with the nitrate per se, and this silver is going to hook up and form an SO4, hook up with the sulfate to form a solid. We have one element here and another element, and they form one element. So you take two items to make one combination. This item here, you'll notice you have a carbon-based compound. You're going to have oxygen as a reactant, and our two products are carbon dioxide and water, so you know that that's a combustion. All right, press pause. See if you can do these for our last round of making sure you know how to identify types of reactions. So on A, we have two items. We're going to combine them together to make one, hence combination. On B, we have an element and a compound, and when we look over here, you'll notice the silver went in, kicked out the hydrogen, and so it replaced it. But the silver, there was only one item that was going in and doing the replacing, so single replacement. On this one, we have a carbon-based compound, and you'll notice oxygen is a reactant, and the two products are carbon dioxide and water, so that is combustion. On D, we have a compound, we have another compound, and you will notice that the first item on each switches places. So our K hooks our positive ion, our potassium, our K, it's going to hook up with the negative ion, the anion, the chloride ion, and that our lead 2 is going to hook up with our sulfate. So two different things switch partners, so we have a double replacement. And last but not least, we have one item that is going to break apart into two or more items, and so that is decomposition.